Hi, everyone. So my name is Gustavo Sandoval, and I work at NYU. Today, I'm going to present you some of our joint work on our research that deals with writing secure code using large language models. At this point, probably everybody has heard about Copilot and large language models. This all started a couple of years ago in 2021 when Microsoft and OpenAI released a limited version of GitHub Copilot. Now, 2 years later, what we have is that researchers and CEOs alike are saying that Copilot will write most of the code. Here's a quote from the GitHub CEO that says that Copilot will write 80% of the code sooner or later. And it's in use by 1 million developers. In our work, we're going to investigate how good these AI models are writing at secure code. So you might be wondering, what's Copilot? What is a large language model? What is the relationship? The way I'd like to think about this is that a large language model is just a statistical model that predicts the next word based on the input, right? So in this case, if we have a large language model, a light blue rectangle, and it's trained to give you C code, and it has this input void, then the next token that it will produce will probably be main. And then we use this as the input and probably will produce open parentheses, and so on and so forth. So the interesting thing for us here is that Copilot has two parts: an extension in your editor and a large language model. So the extension in the editor is what's called Copilot, and it's going to call an OpenAI large language model. What we did in our work is that we built a custom extension similar to Copilot that called the OpenAI large language model, but it allowed us to log more of the user actions with more granularity. And then we used the OpenAI language model. What inspired us was some of our previous works, such as Asleep at the Keyboard, that found that 40% of security-related code produced by Copilot is vulnerable in security scenarios. This is going to raise the questions: are users impacted by the buggy suggestions? In our work, we found that this is not the case, and we find that when a programmer uses AI as a coding assistant, the incidence rates of severe bugs does not increase. In the rest of the presentation, I will go over on how we determine this. So first, to determine if users are impacted, we need to conduct a user study. And this is the first user study that is explored and compared the code written by programmers as a control group to the code written by programmers with the help of AI. So what we're interested in is whether the code written by the humans is better in terms of security than the code written by the humans with the help of AI. Other studies have looked at the functionality, but we are the first that looked at security. So our research questions were: does an AI help users write better functional code? Does AI assistance help or hinder in terms of the incidence rate of security bugs? And how do AI-assisted users interact with potentially vulnerable code suggestion? So in order to research these questions, what we did was we recruited a representative sample of computer science students. We recruited over 100 students, but only 58 ended up having valid submissions. One of the prerequisites for the study was that the students had been exposed to the C programming language, since that's what we used to write the code. And the reason we chose C was because a substantial amount of MITRE's top 25 CWEs, common weakness enumerations, bugs deal with low memory issues. So for our study, what we did is we gave the students a task to write a shopping list application with 11 functions. It used a linked list as the data structure, and we only gave them a description of the functionality and some unit tests. Once all the submissions were done, we manually analyzed the code for functional and security correctness. So here we first can see the instructions that the student get. There's basically the comment with the full description of the function and also the function definition. They were supposed to fill out the function with a correct implementation. What we see here in gray is the text suggestions from our AI extension that would log whether they accept it or not. Of course, this was a student with AI assistance. Now, what the student can do is they can either accept, reject, or accept and modify the suggestion. Here, for example, we see a student that rejected the suggestion and then wrote their own code. Here we can see a student that took the whole AI suggestion I showed you before, and our job is now to figure out if there are any security vulnerabilities like CWEs. So here we see that one of the CWEs that this code contains, CWE 787 out of bounds right, because they're not using SN_printf. We can also see a couple of CWEs 476s, null pointer dereferences. In our work, what we did is we went through all the submissions and did this analysis for all the users and vulnerabilities. So here you can see the overall results in terms of functionality. We assessed the functionality of the code using the unit tests that we gave. Each group had to implement, as I said, 11 functions and pass 11 basic tests. We also created 43 expanded tests that we didn't give to the students. And those tested things like edge cases, such as invalid parameters, null pointers, negative indices, etc. So here what I show you is the per group averages, right? So we can see the average of the functions implemented per group, the percentage that compile, and the percentage that pass the basic and the extended tests. The interesting thing to see here is that the AI-assisted participants have a small but consistent advantage over the control group. The assisted group were 6 to 10% more productive and wrote about 13% more code than the control group. Now, in terms of security, after doing the analysis for all the users, this is the distribution of the top 10 CWEs for all the 58 students. In the first graph here, I'm gonna call out your attention to a couple of them. So the first one that you can see is CWE 787 out of bounds right, which we saw before, which is pretty close between both of the groups. And this was mostly because almost everybody used SPrintf instead of SN_printf, as we saw in a couple of slides ago. Another interesting CWE is 416, use after free. That is the second most severe CWE and is more prevalent in the assisted group. And when we looked into this, it was because the assisted group ended up making frequent mistakes due to the handling of the car star item name on the fields. On the second graph, here on the right, what we can see is the aggregated results. So what this indicates is some differences between the control and the assisted groups. Because of the sample size, what we could only establish with statistical significance was that the assisted group doesn't produce bugs at a rate higher than 10% of the control. And in fact, the average that we see here tends to be lower, but we need more data to establish this. Another of our questions in the research was how do users deal with buggy suggestions? So to answer this, what we did was, with all the data that we had, we wrote a visualization tool for the results. And it explores the LLM suggestions acceptance. So you can see here on the right-hand side, with a black background, the code suggestion from the language model. And on the left is the code that the student wrote. So the first one, you can see in green, the code accepted exactly from the coded suggestion. Here in the second one, we see in orange that the student modified the code to fix a bug that the language model has suggested it had been a while loop, and the student correctly fixed it to be an if statement. So one of the things I want to emphasize here is all the data collected can be a treasure trove of answering different questions. In terms of results, about our 3 research questions. So our results corroborate recent studies that have suggested that language model assistants improve developer productivity. Assisted users submitted more lines of code that passed more tests and completed a greater fraction of functions. In terms of security bugs, well, prior work found that language model assistants may suggest security critical bugs. It didn't examine the tool against human developers. So in our case, we found no conclusive evidence to support the claim that LLM assistants increase the incidence of CWEs. And in terms of our third question, what we found is that most users will blindly accept any vulnerable suggestions. So finally, to conclude, large language model code assistants are going to improve functional correctness in this scenario and do not increase the incidence of severe security bugs for low-level C code. In addition, we want to continue with this work. We have created tooling like our web editor, extensions, login frameworks, and visualization tools that will assist in future user studies, and we're excited to collaborate and to continue with this work. Thank you.